start again. So, well, the last time we were in our lectures, we talked about current in the diet. The current in the diet is initiated by injecting majorities against the electrical field over the barrier, which you reduce by applying forward bias. This injection takes place, and the minority carriers, its concentration is changed by your action of forward bias. So this diffusion gives the device its name. It's a diffusion device. This diffusion to here changes this concentration. It is above the thermodynamic equilibrium. This injected value relaxes in its concentration alongside this tangent, and this tangent is the how it's called? L. Tell me. It's the. Let's go back. It gives the slope. It gives us the diffusion length. Exactly. So the diffusion length is given by the diffusion coefficient and the relaxation time. So the time, how long one carrier does live in this area. So if you have this slope, you have a certain flow rate. And this flow rate gives us is given us by this equation. So the flow rate is defined by the slope times the diffusion coefficient. And as we let flow electrons, the flow rate ends up to a current value, density, times area. Then you have the density, the current itself. As we have two types of components in our current, the hole current and the electron current, the overall current is the sum of them. But to get the full value, you need at one side both values. We are able to calculate at the p side the carrier concentration of the minorities for the electrons. At the n side, we are able to calculate the minority carrier concentration for the holes. But we cannot calculate the current density for the majorities. But we can say that the space charge region doesn't change the current density. Therefore, if we are able to calculate the current density for the minorities here, we can say we have the same current density here. As we have then now the current density here and the calculated one here, the sum of these two values is the overall current. And the overall current is constant, as we know that current doesn't disappear. Okay, so therefore, the total current is the sum of the current densities at these space charge region boundaries, which we can calculate using these equations. And the result was the diode current, full stop. And the diode current, we have also the calculated values in the spreadsheet you have in your download area in Relax. Okay, here we stopped talking because now today we will continue with the small signal parameters of a diode. Let's talk about space charge. And induced by the space charge, the capacitance. Okay, so what is, in general, a capacitor? It is, if you define it by its small signal behavior, it's the change of the charge it stores by changing the voltage. If the capacitance is constant, then it is Q divided by the voltage. But here, as the capacitance does change, we take the derivative. Okay, now how much charge do we have in this capacitor? Um, it's very easy. We have the area, we have the penetration of the space charge, of the depletion area. So what is this? This is a volume. Volume. And in this volume, we have some particles. Which particles? Your dopants. And your doping concentration is given in the space charge region. And if you have the volume and the concentration, you have the absolute numbers, the number of charges. Which charges? Electrons. So we know the overall charge, but we want to have the first derivative of this charge. And if we put in the equation for the space charge boundary here, this equation herein, and calculate the first derivative, we get that the space charge region causes a capacitance which is inversely proportional to the applied voltage. Okay, this means if you increase the voltage you apply, the reverse voltage, you reduce the capacitance. But I want to stress one point. The dependency of this capacitance to the voltage is very, weak. It is under the square root in the denominator. Okay? Keep this in mind. This information is also used by characteristics purposes. How? You reverse bias your diet, and in the reverse polarity, if the doping concentrations are box-shaped, then you get, if you plot voltage against 1 over the capacitance square, then you get a straight line. And from this intersection, you get the doping concentration and the built-in voltage values. And if you interpolate to forward bias to this value, to the intersection to the x-axis, then you get the built-in voltage itself. So by capacitance measurements, you can characterize the physical parameters of the diet itself by just taking this equation, square 1 over, and you get this straight line, how you call that? Geradengleichung. Yeah, the equation for lines. Yeah. No, in mathematics, if you have one line and this line is y is equal to m times x plus a c, then the straight line equation, exactly. So we have a straight line equation if we do this but with this equation. Therefore, you can use this for characteristics purposes. But that's not so very important. The important point I want to have in your mind is this dependence. See, this dependency is used in so-called varactors, variable capacitors, variable voltage controlled variable capacitors. So if you read in some handbooks of semiconductor foundry, then you need somewhere a capacitor you can adjust its value. So diodes are used to do that. Where are capacitors used to be changed in its value? In oscillators. So in each and every oscillator, in wireless applications, in Wi-Fi, in your mobile, everywhere you can think about setting the oscillation frequency and controlling the oscillation frequency. You need a varactor. So you use the space charge in these devices. Okay, so space charge we have additional charges. Um, you know, if you put these charges to the other side, you disturb the equilibrium. So you store here the charge in the volume. This stored charge appears only if you apply forward bias, due to the fact that for forward bias, you just start this injection. So if you want to have a diode to let flow the current, you store charges in the diode. You can't avoid it for PN junction diodes. Okay, let's quantify these values: stored, injected, blah, blah, blah. So again, the basic equation is the same. How does the stored charge value change? By changed applied voltage, but forward voltage. Reverse, there's no one because you don't inject anything. Okay. This charge you can calculate, you can imagine you start at space charge boundary and integrate to the infinity. What do you do? Integrate. The, the change of this injected concentration of these particles. Okay, so starting at xn till infinity. So you go in and count all these charges and say, I have it. In order to have the charge value itself, you need also the area. And we don't need the overall value. We need just the value above, yeah, above the thermodynamic equilibrium value, because the rest is required for neutrality. And the delta is caused by you, by injection, forward biasing. Okay, so this delta is calculated by this equation times Q, the elementary charge, and we know this value also from the equations we have had calculated in advance. So I just copied this equation, put it in, and integrate it, and the result is something very important. I have put this result to here, okay? And I have said, well, -1, yeah. If this value is 2000, then -1 doesn't count. Okay, so the diffusion charge is exponentially dependent to the applied voltage. For sure, if you increase, if you increase this concentration exponentially, yeah, then the charge is also increased exponentially. That's not very surprising, but it has a very dominating effect on your application. If you use a PN junction diode, oh, here is missing one space. If you use a PN junction diode in power electronics, for instance, what is the most simplistic power electronics topology? From my point of view, the most simplistic one is this one. You have an inductor. Here you have a voltage source. This inductor is connected to a switch. Assume here the ground. And then you have here your diode. And this diode is feeding a capacitor here. So that's the most simplistic circuit for power electronics topology. What does it do? If you have here, let's say 5 volt, you can have here, let's say 15 volt. And how does it work? If you switch on the transistor, then the current through the inductor increases because the inductor integrates the voltage, and the result is the current. As long as you switch on, the current increases. So in this diagram for T and the current value increases as long as your switch is switched on. Now you switch off again. Now your switch is open. Then the inductor, its energy is stetig. Stetig is which word in English? Huh? It doesn't change abruptly. What is the word for not changing abruptly? So it can't jump. It can change, but it can't jump. That's not possible. So stetig, you can Google. The current now is reduced and it is flowing through the diode into the capacitor. And if you have some load here, then some portion is flowing here, some portion is stored here, and so on. So in equilibrium, you have voltage translation for V out to V in is 1/1 minus D, so on and off time. Okay. Why is a PN junction a problem? If you switch on, this diode is 15 volts, 0 volt. It is reverse biased by 15 volt. Okay, doesn't mind, it's okay. Now you switch off, the this node is pumped up by the current, And this diode gets its forward voltage so that the current can flow. Now, this diode stores your diffusion charge. The diffusion charge, which is linear to the current and exponential to the voltage. So as high, if you increase the current value, you increase the charge value you put into the diode. Then you switch on again. What do you have to do with this charge? You have to discharge into the ground. So each and every time you switch on again this transistor, you have to pour out this Q before you can have this capacitor, this Q space charge capacitor, to get at 15 volt before after you have poured out the charge. And if you increase the frequency you are switching this transistor and this diode, you can burn these devices without having much application here. Therefore, the silicon applications are very dependent on the current level. Let's say your current level is 5 amperes. It's not much. In the time you are switching on again, in this time period, within some nanoseconds, if this value is 5 ampere, in this time moment, your current can be 30 ampere and comes back. You have spikes for a short period in time. And this current is flowing through your transistor. So if you assume you have to carry only 5 ampere, you are burned. You have to let through this Q first. It's like the weather, you can avoid it. You can compensate for following. You calibrate in your application the switching frequency. So because you know the Q and the frequency, then you know the energy you lose. Okay? Fair. Point one. Point two, you have to let through this current, the high value in this current. So your transistor is dimensioned larger than you require for the application itself. So both actions are done in power electronics. But I just wanted to tell you this side of these electronics. We are now responsible to understand what the devices are doing. Okay? But in power electronics, you get more onto your ears about these topics. But later we will learn how to apply different types of diodes, Schottky, which don't have this Q diff. So Schottky doesn't have this Q diff. Okay? But it will come. Before we go to this, let's take a look at Wikipedia. There I have taken a picture out of their library. It's just 9 mm long, this diode. You know these diodes in this shape, so in this shape. And within this diode, you have the diode. It's here. So this is your, let's say, PN junction. That's all. The rest is copper. And here, tin. So in order to handle it. Yeah, handling. And these are the tiny wires, you know, the tiny wires. So these fat things are the tiny wires. So your thermal resistance is this wire. So yeah, that's it for the PN junction. Short words how you produce this. You have a wafer. One moment. Yeah. You have a wafer. On the wafer, or at the surface, you put on a liquid which consists of the p-doping materials. You flip the wafer. The other side consists the n-type doping material. And then you put these wafers into a wagon, a quartz glass wagon, close it, and put it into an oven. What does happen with these dopants from the surface? They diffuse into the silicon. This diffusion does take place if you weaken the bonds of the silicon. And this happens at above 1200 degrees C. Then the diffusion takes place. Sometime you require that this happens. And after it has happened, well, it's in. Now you take this wafer out, thin it down to the value you require. You know the space charge region and so. Hmm? The doping level is a function of the voltage level you need to withstand. You know this V-shaped electrical field, and the maximum is in the center. So the doping concentration is given. The thickness you define by thinning the wafer. And then the most important thing happens. Um, you saw it in a chessboard structure through the p-n junction. Then the sawing Graben, sawing Mesa, the side walls, you have the p-n junction facing the surrounding. Now you have to put on some oxides to passivate in order to prevent the leakage there. Because there the crystal structure is not present anymore. No crystal structure, no theory of band gaps. So you have at surface a good path for leakages. If you passivate it in a plasma oven, then now you can break out the chess board structured silicon pieces. As large you do this, as high you get the current through the diode. So these types of diodes are cost cents, some cents, 1 cent, a portion of a cent, because it is mass produced this way for power electronics. Okay, so if you go to, let's say, the company Diatech, I think they have yet their manufacturing facilities in Germany. I have seen this in their facilities at Diatech, which I'm now talking about. Now let's go back to the lecture. I have switched again all the topics in my slides to questions. So these questions can be answered going through my slides and going through the spreadsheet by playing around with it. So the answers you have already. Now you get the questions. Okay, so these questions are quite interesting from my point of view. Now let's go towards other types of diodes. To start this procedure, we start to think about metal vacuum junction. Think about metal. This is a metal. So you have a piece of metal in your hand. You look on it and say, yeah, metal, it's neutral. And in the metal, you have for sure electrons. The Fermi level is above the conduction band edge. You have electrons without the need of temperature. You have electrons in excess. How you get these electrons out? Mechanically. You take a hammer and smash it. Yeah, you see it. Then you get these sparks. But that's very brutal. You can do it with higher temperature. You heat it up. So it's also mechanical, but in the material itself, by vibrations, by phonons. Okay, then you have a dust of electrons around this metal, but they keep there. They don't fly away. They keep at the surface. Let's talk about the energy you have to overcome to have these electrons, which are free but keep there at the surface. And this energy level is Q times phi, Q phi. It's the so-called work function. If you have a polysilicon is heavily doped silicon, which is not monocrystalline. It is roughly 4. If you have aluminum, 4.2 volts. If you have copper, 4.4. And the highest value in this table is for platinum, 5.4 volts. So this barrier you have to overcome, referenced to the Fermi level, is this value, to the vacuum level. What is called the vacuum level? It's the level to free up an electron into the space. Okay, now we have some work functions. And the Richardson constant combines the current with the temperature and the area. It's like the Boltzmann constant, which combines the energy to the temperature. And the Richardson constant combines the current level to the temperature, which has a linkage with square. If you have now also for the metal density of states, which is also parabolic. If you have the Fermi-Dirac statistics for the metal you heat it up really, so it is glowing red. You generate some probabilities where you have states in the vacuum, and the escaped amount of electrons is this area here, this area. Okay, and if you calculate this and say, I can have these electrons somehow for current production, then I can calculate the current density with the Richardson constant times the temperature to square. You know in its units. Hey, Mrs. Akbal is coming in. I don't know how long she has waited. Sorry again. Uh, the units of the Richardson constant was ampere per temperature square centimeter square. And now if you calculate it with T square, then you have the ampere per area. That's the current density. Okay? And it is exponentially dependent to the work function. For sure, this amount of electrons you have available at the vacuum level is dependent to this distance, and it is exponentially dependent to this distance. We learned from the Boltzmann approximation. Therefore, again, the exponential behavior of that stuff, T, deleted. It's Kelvin. The unit is not T. The variable is T. The unit is Kelvin. Sorry, I've just looked here. Therefore, I have seen my error. Okay, let's go ahead. What we have learned, not much. But this type of diodes are used in vacuum tube diodes. If you have a cathode which is activated by temperature, let's say you have a vacuum tube fluorescent light tube. You have always some windings of metal which is heated up. Then you have to suck these electrons with high voltage out of this area. They are accelerated in this electric field along the tube, and these electrons does smash to the fluorescent layer in the inside of the tube, which you see is a white layer. And this electron uh, excites some state in this fluorescent material. And if these excited electrons relax again, they emit photons, which we say light. So this dust of electrons are accelerated within the tube. They excite electrons within the thin layer, the how it's called, fluoreszierendes Material, fluorescing material, and the relaxing is the light. Okay, but that's not our topic. I just wanted to say how we work with electrons. Now let's take the same ideas to the semiconductors. To do this, we take again the silicon substrate and put in some dopants. We make an N-well. And the P junction we substitute with a metal and call it anode. And this metal builds up the Schottky contact. So now you can say, one moment, we have here also metal and call it ohmic contact. What is the difference? The difference is very large. If you have here a metal, you put this metal first. Then you heat it up. After heating up, some parts of these metals diffuse into this semiconductor and makes this area high doped. What we have said about high doped areas, they are metallic, degenerative doping. We have learned that at the beginning of our lectures when we talked about doping. If this doping level is so high, it is higher than the states which are available in the silicon. One light just switched off itself. Now it's switched on again. I have a smart home. No, not yet. It's really interesting. One LED, I have bought it from IKEA. It's a smart home. You know this stuff? Hmm? I have linked it to Hey Siri, and I say Hey Siri, switch off something, and then it happens. Have you also stuff like that to play around? Ah, okay, okay. One moment, please. As we are here now, I want to give you something to play with. One moment. I have prepared something, I think, here or here. Yeah, it's here.
Yeah, it's here.
So you
So you
see
see
my
my
handy
handy
camera, my
camera,
mobile
my
phone
mobile phone
camera.
camera.
Yeah,
Yeah,
okay. Now
okay.
I go to
Now
the
I go to
ceiling.
the ceiling.
You see that?
You see that?
So these
So
panels.
these
Now,
panels.
one
Now,
moment,
one
please.
moment, please.
Hey
Hey
Siri,
Siri,
Arbeitszimmer aus.
Arbeitszimmer aus.
So the
So
ceiling
the
is on.
ceiling is on.
Hey Siri,
Hey Siri,
Arbeitszimmer an.
Arbeitszimmer an.
It has
It
worked.
has
So,
worked. So,
and one of these panels uh, just switches off and on, and nobody is playing around it. I don't know. You are guilty. Okay, so come back to degenerative doping. So this area is really ohmic due to the high doping level. Okay, but then you place the metal. And then you never heat up this wafer again to values, let's say about some 100 degrees C. So in the manufacturing process, you have a thermal budget. When, to which time? No, the left one switched off. Okay. Okay, switched on again. Um, then you have the Schottky contact if you don't heat it up. Therefore, you can say Schottky diets are somehow more empfindlich, sensitive to, it's more sensitive to temperatures above some 100 degrees C. Okay, but physically. And the structure itself, it is also a diet structure. And by Dean norms, these lines look like this. You remember for p-n junctions? Have you memorized the symbol? It's just like this. Okay, so adding to additional pieces of lines, you have this symbol. Okay, now let's go to the band diagram. It is important. Relax, it's not in steady state. Ah, really? I don't see anybody. This person should try again. Okay, I will put one eye to the participants list where the waiting room person will pop up. Um, we're not in steady state. That means we have a constant vacuum level. Steady state, not in steady state means you have not banded vacuum level because here the vacuum level it's defined by getting free something. For the metal, we have this work function. For the semiconductor, we have this work function. So the work functions define the energy where the Fermi levels are situated. One. Second, the band edge to the Fermi level defines the potential barrier to get free into the semiconductor. Because first we said, let's take these electrons free to vacuum. That's the vacuum diet. but we can also free it to the conduction band. Now there we have also states. Okay, so let's take a look on the Fermi-Dirac statistics for the semiconductor and the Fermi-Dirac statistics for the metal. If we combine them with their density of states, we get this amount of electrons in the metal, which are above this barrier, and in the semiconductor, we have this amount of electrons. We're not in steady state, and nobody is in the waiting room yet. So what happens with... Oh, okay. I see. I see. Just give me a hint if I oversee him in the waiting room. So now we have these electrons, and these electrons go to here. And these arrows are the technical current direction. So electrons go here, the technical current density is there, vice versa. Okay. And if we are in the steady state, in the thermodynamic equilibrium, then the Fermi levels are aligned. The amount of electrons on both sides which are available for injection from left to right and right to left are equal. Now we have this new equilibrium, and there, due to this movement of these electrons to here, your space charges are left over, like in the p-n junction. And these space charges build up the space charge region. But now we have only one space charge region, namely in the semiconductor. In the metal, as the density of electrons are infinite, you have no band bending. Everything is straight compared to the semiconductor. Okay, now let's take a closer look at the band edge, at the Fermi level edge, and the conduction band edge. Only these three are now, at the moment, important. What do you need for the electrons which are here as a dust to go here? They have to overcome this Schottky barrier. Okay, what happens if you heat up? This amount of electrons increase. What you need for the semiconductor to release its electron dust to here more than in the equilibrium. You have to change this bending. You can have a following image in your mind. You have this cup, and if you want to have this fluid at the other side, you have to elevate and pour it out or pour it in. Yeah, and this happens if you apply a forward voltage. You pour out the electrons to the metal. That's forward biasing, a Schottky diode. And this is the reverse bias current. Now you know that due to the barrier height and due to this current density with the Richardson-Dushman constant, this current into the vacuum, or in this case, into the conduction band edge, to the neighboring semiconductor, is dependent quadratically to the temperature. And that's quite bad, but it's fact. It's physics. Therefore, Schottky diets are not only physically for degenerating its physical properties, sensitive to temperature. Also, the reverse current is very sensitive, proportional to the square of the temperature. Okay, so if you take a Schottky current, you say, I have, yeah, what we are talking about at the moment. The electrons in the metal are majorities. The electrons in the N-type semiconductors are majorities. You don't have this lazy, slow diffusion process. You don't have the recombination time you require to take place. You don't have to evacuate all the charges you have accumulated by forward biasing. Nothing. You don't need anything. You just push around the majorities, and that's fast. So Schottky diets are very fast diets. But these are qualitative statements. Quantitative statements we have here. Now, the Schottky barrier is a function of the work function here, and how it's QS called. Do I have written it down? QS is, I have forgotten to place the name here inside. That's also the work function. XS, I wanted to say. It's the Elektronenaffinität, the affinity of electrons. It's referred to the conduction band edge. The work function is referred to the Fermi level, and the affinity is referred to the conduction band edge. Now let's take a look like in electrical engineering first semester. You have the sum of the voltages is zero, and that applies here also. The work function here plus the doping level plus the electron affinity is the built-in voltage. And this information is used here. The built-in voltage is exactly, okay, the Schottky barrier is defined here, and the built-in voltage is defined based on the Schottky barrier. And the Schottky barrier you can measure as a function of a pair of materials. Why a pair? Because it is defined through the linkage of two materials. This means silicon to aluminum, it is 0.5 to 0.7 volts. If you take copper and silicon, you increase this barrier. But as I said, as you just put the metal on top of a naked surface, where the crystal structure has stopped existing, it is very sensitive how you pre-condition the surface. Therefore, Schottky barrier diet production is very sensitive to everything. Let's talk about an anecdote about Atmel semiconductors in Heilbronn. Previously, they were named TIMIC semiconductors. Okay, at the vicinity, no, they are just producing this type of semiconductor materials for integrated circuit applications, for automotive, for instance. And one parameter for surface potentials have changed. They haven't found anything not in the pipes, not in the liquids, not in the materials that they are using, not in the semiconductors, not in their pre-treatment. No, no, none of these tests have produced any change. But the Schottky barriers, let's call it the Schottky barriers, have changed. What has happened? In the vicinity of this uh, foundry, there is Maggi production. You know Maggi? You pour it into your soup for spice? Yeah. They have changed their recipe in the neighboring facility. And the particles in the environment have changed. Therefore, the conditions in the foundry has changed a little bit through all the filters which they usually, for sure, in the clean room they apply. So all changes in the environment does affect the surface. Therefore, manufacturing semiconductors not only applies to control your environment in your lab, you have to control everything in your environment to keep everything constant. Okay, so some people say they color the current they put through the wires the same way, but sure, it's just a joke. Okay, so now we can calculate based on the Schottky barrier your built-in voltage, and the built-in voltage again depends on the doping level, like in a p-n junction, but only from one doping level. You remember, this is the density of states in the silicon. This is the number of places for electrons in silicon, which can be occupied theoretically. And the space charge region width is now only dependent on one value. If you take this equation and compare it with the p-n junction, you get this equation if you increase the p doping level to very high values. Just take it in your preparation, in your, how you call it, not preparation, but in your going through these materials yourself after the lectures. Just take the equation of the space charge region for the p-n diet and let increase the p doping. Then you get this equation for sure. The built-in voltage, yes. I don't know. We have to define it ourselves because we will do our exam orally, and the written exam period is, let me take a look. The written exams start. I have in my calendar the 24th of July. Is it true? Do you have? Okay. So we will define some day where it is convenient for all of us. It can be during the lecture time. It can be after the lecture period. We will sit together, make a date, one day, and then we will go through the exams. All of you, I will have for 20 minutes in questions and answers. A second person will sit in this virtual room and do the protocol. All of you need to have activated your camera. Without activated camera, through all the time, it is not valid, this exam. So prepare yourself also technically in that way. And yeah, that's it. And the only hmm? You can have everything to your hand. Except, except online connection to different people. Exactly. But I have to rely on your honestness at that point. I cannot control that. Books are free, your lecture notes are free, everything is free. So I, yeah, exactly. And if you haven't understand the questions, you ask back. Yeah. So that's the convenience of oral examinations. You don't get, yeah, again? Oh, perhaps very simple calculations, and then you can show it to the camera. But the qualitative statements are the most important ones. The quantitative you have on your Excel sheet. You can take there a look. Because if you can say the space charge region depends on the square root of the voltage, then I'm happy. If you know that the excess concentration is exponential to the applied forward voltage, and why it is the case, I'm very happy because you have understand the mechanism in the semiconductors, and that's the aim of this lecture. Okay, great. Not at all. Uh, again, the question, please. You can really picture by uh, um, a test examination question. What can it be? What are the small signal characteristics of the diet? Okay, the small signal characteristics of a diet is for the current V to the voltage to the current, it's an exponential one, and the small signal is the slope of that. Slope is the first derivative of the current equation. First. Second, you have without this, you have the capacitance of the space charge. The space charge region has a 1 over square root of the voltage as a small signal characteristics because you calculate it with dq for dv. And the third one is originated by you. This one is given is proportional to e to the power of v divided vt. Why? It is only varied for v larger than 0, and v is defined from p to n area. So these are the small signal parameters. If you know this by heart, then I'm happy. And then I can say why you don't have this. Then you can say, oh, diffusion capacitance just occur because of the lowered barrier and injection. And so you explain it to me, but only one portion of that topic. So examination. Take some questions of that because I have just these topics talked, explained to you. Okay? Great. Not at all. Anytime. Um, okay, here we have this. We have this. Now we go to the point why we additionally use Schottky diets. Because of that. A typical PN diet, this curve is copy-paste from the Excel sheet. I have used, okay, don't you do it with hands and fingers. Let's do it with the real sheet here. One moment. Let's go to not PN diet. Let's go to no vacuum diet. One more. Schottky diet. I have plotted with the same values we have generated the PN diet. I have used these equations um, for the N-type semiconductor. For the built-in voltage, we have just taken a look on how we calculate the built-in voltage, the space charge region, and the diet characteristic itself. We haven't learned that yet, but we see the result. The direct result is that you can analyze it on your spreadsheet yourself, copy paste this image to my lecture notes. We have the same current level at a much lower voltage level. That's the reason, the main reason why you use Schottky diodes. Okay, and if you would go to these voltage levels, you have infinite current. So you can't go to these higher number of voltage values. Okay, how we get the current into the diode? By calculating the current level from the metal into the semiconductor and the current level from the semiconductor into the metal. From the semiconductor into the metal, we have this as a value. From the metal to the semiconductor, we have just the Schottky barrier. And the sum of them, or minus of them, depends on the direction, we get the overall current. And the overall current is defined by the saturation current. Now it is dependent to the square of the temperature. Why? Because this value is this current to this direction, and this is defined by this barrier height, okay, times whatever here. Now you can reduce everything to this equation. So what is an exponential equation? This one. Like the interest rate on the interest rate. Let's assume this is an interest rate equation. And this is a rich guy. It has a very high starting value. And the PN diode is a poor guy. It has a lower starting value. But at a given forward voltage, that's your lifespan, you reach some level of luxury. So the rich guy reaches it very early and it goes to infinite. The poor guy keeps on very low values. It's an exponential function. And perhaps in lifetime you get a certain value back from your bank. That means everything is related to this saturation current because the multiplicator, this term, is the same for both diodes because your applied forward voltage is the same value as a figure. Okay, so the changing value is this reverse current, the saturation current. It's a million times higher than for the PN junction. Therefore, you have for lower forward bias values a high current. And here you have this explanation. It is a microamp value, not picoamp. It's a microamp value. Okay? Let's calculate this value for 0.2 volts. Let's take the calculator, pocket calculator. VT, let's assume 0.259 volts. 0.2 divided by 0.0, so, huh? I have mistyped. Do you have the result? I have it. 2256. And due to the high number of the saturation current, the resulting diode current is 17 milliamp. Let's compare this calculation to the PN diode. We have done that also there. You remember? If you have 0.2 volts, this value, oh, okay, I have used a different thermal voltage. It's also in the range of 2000. But the resulting diode current is nanoampere with the same area and the same N-type doped material. And the reason is the poor guy. The reverse current is picoamp. But the poor guy has also an advantage. If you have to have reverse biasing at high voltage levels, the power level is very low as an excess heat. Point one. Point two, this current level keeps low and is not exponentially, quadratically increasing with temperature, like you see it here. Therefore, if you have a hot environment, you can't use a Schottky diode, although you would require the low voltage levels. Therefore, you have to define where you need it and where you can't use it. But let's go to the next step, the space charge. We have no diffusion capacitance. Therefore, in all radio frequency applications, the diodes you use are Schottky diodes because you can forward bias, reverse bias it billion times in the second. Okay? And PN diodes doesn't work due to the stored charge. Now you say, now I come back, Mr. Bota, to your question. What we do with this problem? We use here a Schottky diode, but not in silicon, but in silicon carbide. Silicon carbide has a wide band gap. Having a wide band gap, you have a high Schottky barrier. Having a high Schottky barrier, your reverse current is not so high. But you have a forward current without stored charge, without a diffusion charge. Therefore, in applications where you have to have very high efficiency, you can afford to take the silicon carbide diodes, which are a little bit more expensive. Let's go to DigiKey. It's written DigiKey. It's a worldwide distributor. And just compare for high number of devices to buy, not very low numbers, not one. Let's go to 100,000 devices to buy to find out the value for the buying, the price. Yeah. Sorry. And then you see how much a comparable fast silicon diet does cost compared to silicon carbide diet. Do it yourself. It's not a topic of examination, but also it's very, very interesting for application. So that's it for our Schottky diet. And all the questions you can imagine about the Schottky diet is in this area. Mrs. Akbar, your oral examination questions. So that's it for today. In the morning, I wanted to talk about semiconductors. Now I say we take a break till 2 o'clock. Okay, let's take a good break. Let's take a good lunch and see you again. Breakfast, that's also a good idea. See you. Bye bye.